Okay, here's the setup for a big tornadic supercell day in northern South Dakota. Pretty much just a lone event, basically. Here's the 500 millibar trough at 7 p.m. that day. You see it's this humongous trough out in the west. It's like one piece of energy is rotating up here, and then another one's digging down here. And this one will cause a second area of low pressure to form over South Dakota as there's another up here. You can see the temperatures aloft are given in these red numbers, these dashed lines. Colder air is coming in aloft with the trough. You can see minus 32 Celsius out there in the middle of the trough, where it's only minus 9, minus 10 out here, and it's all getting shoved east. The storm's going to take shape up here in almost north central South Dakota. So you can see that colder air aloft was just spreading over where the storm fires. We had a surface low in the middle of the state forming, and then a boundary, a warm front up here, and then a dry line coming south, and it's formed at where those two intersected, or the triple point, which is often a favored place. The one thing to note is just right here, that's almost southerly in the mid levels, and this isn't too much further. That's pretty much your steering height, and that's getting kind of far to the south, better southwest, flatter because you're sheer unless you got due east winds. But anyway, just remember the mid-level steering is kind of almost from the south-southwest, not quite southwest here. You got one piece lifting up here and another piece of this trough digging down here. It'll create the second surface low that's of interest to this chase day. Like mentioned earlier, 700 millibar is often an area you can look at to judge your cap, how hot it is aloft. And 12C in middle of June is pretty warm. 15C, you're not going to break it. Just too hot at that level. So 12C is really close. So that was a big concern this day, as the cap was progged to get advected northeast ahead of the low. And you can see, I showed this earlier, but this is morning. Kind of follow these lines. It gets colder out here, and these get warmer. You can follow this bulge right here. That's pretty much the hottest air, like the 12C line, and you can watch what it does. So I switch it to 7 p.m., 7 a.m. Now we're at 7 p.m. You can see how it shot clear up through Minnesota. That's your cap. That whole bubble is a hot air cap ahead of the system blowing north on these winds. Again, it came off the higher terrain where the temperatures are higher up and the ground's higher up, so your temperatures are warmer, and that just gets shot out above your warm sector and caps it off until it gets colder aloft as the trough moves further in. You can see it shot up this way, and it's just kind of getting pushed east of where that storm's going to fire. But it was a close deal on the cap. I'll go back and forth here. Bam, it shumps up there. Again, and notice the bigger number is actual Aberdeen's balloon, actually read 12C at 700 millibar. There's a 16, I mean, that's hot. 14 North Platte. Anyway, it's right on the verge. A lot of people weren't real sure a storm was even going to fire this day, but those that chased really got rewarded because a big storm did break the cap. Just went crazy. Here's the same day again at 7 p.m. upper chart. This is actually the lower levels. It's 850 millibar, about 6,000 feet up. You're still down in your moist, warm sector air, the low level air mass. You can see with that big trough out here, see the low levels flow better now. You're getting down lower. This is 850 millibar again. There's a low up here with that first chunk, and then the next chunk's causing another area of low pressure trying to form down this way. Surface low, the further all the way down to the ground. Surface low is getting centered around central South Dakota. But anyway, you can see all these higher green numbers are dew point air. 17 Celsius dew point at 850 millibars is a lot. There's a 20 there. See, this whole area is coming off the Gulf, just nice, rich, deep, good moisture. Look at the barb. Here's Aberdeen itself at 7 p.m. The storm's just west of there at 7 p.m. Due south, low-level jet, 6,000 feet off the ground at 40 knots or 45, 50 mile an hour. That's really good. But remember the mid-levels I showed, how they were south-southwest. So there isn't a whole lot of turning from the mid-levels 18,000 feet down to this low-level jet height about 6,000 feet. There's not a lot of turning. There's some, just not a whole lot. Where there was turning was once you get down to the surface, the winds were a lot more turned towards the east, so you had a lot of turn from the ground up aloft and speed shear. And there'll be a boundary that the storm goes east on that turns it. The mid-levels are trying to blow it, across that boundary, but the boundary is kind of guiding it and turning it deviant so it gets more shear, storm relative. But as it turns east, it's really getting bended better with those mid-level and upper winds coming more from the south. But sometimes you get too much flow and it'll just go across the boundary and go into cooler, stable air. Usually it'll elevate itself. The base will go way high. But anyway, this one anchored on that boundary and went crazy as it went east on it with this strong low-level flow. And finally, on the upper air charts, here's 300 millibar, roughly 30,000 feet, getting closer to the anvil level this day. You see this big trough out here with that too. See the jet streak, the core here. That's hard to see what that is, but it's like 90 knots or so. Yeah, because that looks like 120 knots. Yeah, 120 knots there. That must be 95 knots there. About 70 knots there, but anyway, you got plenty of flow coming in. It's just barely coming into that area too. Just barely getting into there, but you're getting enough flow aloft to help vent this storm. It's going to fire in northern South Dakota. And again, the front left quad of this jet is a big area of divergence aloft where the winds spread apart. So is the rear right. It's kind of hard to find that, but you can see all the divergence in yellow back here and up here. Sometimes there's be sinking on this side, but there's been a lot of good events more on this side, so you're still pretty good to go usually. Now here's Aberdeen's actual sounding, 7 p.m. that night, which was just east of the storm at that time. So you can see the virtual air temperatures needs to be warmer than the actual. But once it goes up, the air above needs to be colder. So if your virtual temperature gets to be colder than the warmer air, it won't rise. So you want the actual temperature that's in the atmosphere, this red line, be colder to the left of your air that's rising. And you can see it's right on top of it for so much of this low level that it's capped. And even if you use this version of the virtual temp line, there's 90 sin. Quite a bit of sin down low. But the thing to think about here is this. 700 millibar temps at Aberdeen were around 12C. You can see, remember on that chart there it said 12C. You can see right here, follow this down, you're right about 12C where it crosses at 700 millibar. But the storm fired a ways west of Aberdeen where surely the air aloft was at least a little colder. The surface temperatures are probably even a little warmer too. So the air out there was less capped where it fired than what the sounding in Aberdeen shows at 7 p.m. But you can see a lot of this on forecast soundings on models. You'll look at those a lot. And as long as they're close to what actually is going to happen, you can get a pretty good idea just looking at those soundings and how the moisture depth is and how the capping looks. If it looks like it's borderline like this day, you might have stayed home, but borderline can still go, That's what it did this day. It was a strong cap, but it was just breakable out there, and the surface convergence helped along the triple point because there wasn't as much heating. There was more heating down the dry line, but the surface flow wasn't as good for tornadoes down the dry line. The dew point spreads were higher, so I'll show that here in a minute with the surface map. But anyway, there's the sounding in Aberdeen, which works out pretty well because it's just right by there. But look at the shear though. This is going up. Surface is the first barb down here. And by 850 millibars, you can see that south at 40 knots. Surface was about east-southeast, southeast at 10 knots. Then turns 500 millibars is still kind of south-southwest. You get way up aloft, you're blowing even harder, 70 knots. All this is 70 knots turning to the southwest. And the storm moved east. So if you can imagine a storm moving east, you get jammed from the south by this low-level flow. And it's getting fed great. And since it's moving east, it's leaning over. These winds are from the southwest aloft. updraft starting to lean over that way. Is it, even though it's going east down this boundary, so it's leaning over and it's being blown away from where the updraft base is. It's just getting fed strong near the ground, and it's sharp, fast turning too. You go from east-southeast surface to 40 knots from the south at the low-level jet height, about 6,000 feet. That's a fast turn. This thing was just primed to do tornadoes, and that's what it did. Here's the surface plot for about 11 a.m. that morning. One thing to note is anytime these circles are filled in like that, it's cloud cover. Or these are more clear, wherever there's like clear, clear, cloudy, cloudy. And then if there's a partial, like up here, it's 3/4 cloudy, basically. That's what that is. If you look on here, you can see your surface low. You got to put the 9 in front of that, so it's 993.8. Whereas if you're over here, it'd be, put the 10 in front of that, because it's not 9. So it'd be 1007 millibars, 0.3. Anyway, 993.8, 994.5, 992, 993. So your surface low is somewhere out here, and it's moving up this way, and it's deepening. So your dew points are all pretty good for early morning at mid-60s. But there's a bunch of clouds over here. And now note these winds. You got all south, southeast, south out here. But notice right here, you hit this wall of easterly winds, cooler temperatures. Well, storms were just rolling through here. They left an outflow boundary, and it shows up on this surface map at 11 a.m. And that outflow boundary was going to be the key. You get your surface low deepening out here, outflow boundary connects to it, and it just becomes a warm front basically as it lifts back north with this deepening surface low, because the surface low will have a dry line, cold front further west, and then it'll have a warm front to the east of the surface low. But this outflow boundary just kind of reinforces that warm front idea. And you can just see how sharp that is. Bam, you hit a boundary, and you'll see this on satellite in a minute. And this was the key to that day. Now watch when I switch it from 11 a.m. to about 5 p.m. See everything south at 5 p.m. So that outflow boundary moved up here. Harder to see on surface now. See the air at 5 p.m. 78 over 66 in Aberdeen, 87 over 68 down here, 90 over 67. You see your west wind here. Surface is 990 now, 990.2. Your surface low is in here somewhere now. Just probably east of there, obviously, because you got the west wind behind the low. So that surface low is in here, lifting up here, and the storm's going to fire in here where that outflow boundary came over and connects to the pretty much the dry line coming down from the surface low. Sometimes you'll get a big feedback area too back here, but anyway, it was a really obvious target that day because of that surface low and outflow boundary connecting. You get better convergence when you got two fronts. Basically, you got a front here and then the front with the low down here. You get a lot of convergence in there. It helps if there's any capping left down low, it can help force it up through there. And the reason the dry line don't work as well is, remember that steering, the mid-level flow is kind of out of the south-southwest. Well, these winds at the surface down here were kind of just southerly. The dew point spreads are getting higher. So you get higher bases, and when those rain, they just rain, and that evaporates easier in the drier air, and you get more cold air forming because of that. And when you get that flow along the boundary in the mid-levels, more than, more crossing it. If you have mid-levels coming this way across the dry line, you get storms to fire and then move off the boundary. But when they fire along it and the flow is along it, they just tend to make more and more storms until you have a big line. You don't want the flow aloft along the same orientation as the boundary. You want it to cross the boundary. Unless it's a warm front, you don't want to cross the boundary too much and go into colder air, but you have back low levels in that case. So this was just a crazy thing that it actually did not cross that front terribly bad. It just pretty much rode it and maybe crossed it a little bit. This was a really strong boundary, and the storm just wanted to go along it, just anchored on it, went east. Here's a full day satellite loop of that day. You can see out here in the west how it spins out there. You got this flow coming here. Your big trough is out in the west. And now watch in the morning. This complex over here is moving east. Look at this outflow boundary that trails back off of it. That's what you could see on those surface obs. It goes out and connects near where the storm fires and the surface low deepening in here. Again, you got your surface low during the day trying to deepen here. It's clearing out warm air. Dry line is down through here. You can see storms fire on the dry line later on, about the same time really, but there wasn't as good shear. The dry line is lined up like this, and your flow is like that. The surface winds were kind of like this, but up here the surface winds were more backed. The storm is going eastward on it, whereas these are kind of going northeast along that boundary with that flow. This one, the storms turned east on the boundary that was up here. See it blowing up right there, and it just goes crazy. And then when you leave in the morning, like I left from down here, it looked like it'd be further south that day. Actually, I was already up here probably by the time 11 was around. Anyway, you don't know how it's going to clear out. You don't know if clouds from the west are going to come, cover the boundary and keep it from getting heat. It really needed the heat with the strong cap. You just don't know a lot. You don't know how far north this front's going to lift before the storms fire. And it was a close one. Here's the Bowdle tornadic supercell. Here's Aberdeen's radar. So Aberdeen's right about here. See, when this thing first fires out here, that's a dry line here. Kind of a bulge to it there, but you can't really hardly see that warm front in that boundary. But it was through here, and it was helping back the winds ahead of this. So this storm, you see the hook right there. That's a precip wrapping around the updraft. But remember the flow aloft. You can see all these storms down here. They're going with that flow in the mid-levels. They're going. Remember the mid-levels are from the south-southwest. That's the way they want to go. But this thing, you can see it's going that way, but then it kind of still turn really deviant. So the shears just totally increases when it does that because it's vented better aloft when it's going this way. And it's going right into the low-level winds that are coming from the southeast and east out here. Tornadoes right as soon as it gets that ball, before that first blob of storms hits it. And a lot of storms, they wrap rain and fill the tornado from their own rain. But sometimes, like this, there's storms firing and dumping into it. They keep raining into where you're trying to watch the tornado. And that was really the problem on this one. You see right there, it's doing a big tornado. Then it gets hit with rain. Then it does some more tornadoes.